Experimental analyses of hermit crab behavior, aggression, dial variation. The amount of aggressive behavior shown by any group of organisms may vary throughout the day. The dial variation of 3 activities has been described in earlier sections for all species studied except Clibinarius vittatus. The pattern of variation in aggressive activity shown by the various species for the most part follows the variation pattern of locomotor activity. This is to be expected if the psychological aggressive level, state, of the organism remains approximately constant. Thus, with a constant level of aggressive predisposition, the variations in the number of meetings, directly proportional to locomotor activity times density, the latter remained constant in these measurements, would produce the observed variations. Dominance orders. The fact that some of the species studied maintain a degree of group solidarity in the field made the existence of more complex social arrangements seem possible. In particular, the size and apparent arrangement of the groups of Pagurus miamensis suggested looking for the presence of some type of dominance order. It was decided to examine groups of Pagurus miamensis, Clibinarius tricolor, and Calcinus tibicen for such social structures. Groups of 20 individuals were established in small glass tanks with fresh sand on the bottom. The members of the group were marked on their shells with colored ink so that individual recognition was possible. Admittedly, this method had the distinct disadvantage of marking the gastropod shell and not the animal itself, and undetected shell changes may have contributed to incorrect observations. However, marking of the animals and, in particular, subsequent detection of any such marking was deemed highly impractical. Following removal from the storage tank and individual marking, the 20 crabs were placed in individual containers for 3 hours. This isolation period simply provided some degree of standardization with regard to the social interactions of the individuals just prior to the beginning of observations. That is, just before observations of its interactions with other individuals was started, every crab had the same history of aggressive interactions. The specimens were then introduced into the observation aquarium. 5 minutes later, the first observation period was started. On the first day, 2 half-hour periods were carried out in succession. During these periods, a record was made of every aggressive interaction that took place between members of the group. In the case of the first 2 groups of Clibinarius tricolor and of Calcinus tibicen, observations were carried out for the next 5 days without any alternations. With the other 3 groups of these 2 species and the 5 groups of Pagurus miamensis, a different sequence was followed. On the 4th day, 5 minutes before beginning observations, the group was placed in a similar but different aquarium. This transfer simulated the change in environment that the group had experienced on initial introduction into the first aquarium, but without the handling involved in marking and the isolation between marking and placement in the tank. Observations were carried out on the next 2 days without special treatment. On the 7th day, about 3 hours before the observation time, the specimens were isolated following remarking when necessary. Even when remarking was not required, the specimen was handled and dried as if it were to be marked. After 3 hours of individual isolation, the group was reunited and observations carried out on that and the following 2 days. This gave a total of 9 days and 5 hours of observations for each group. All groups were observed at the same time each day, and all periods were in the afternoon, 1400 to 1600 hours, shortly before the species being observed normally made its daily migration, i.e. when the crabs were more active. After the ninth day, the size of shell, length from base to apex, length of cephalothorax, and sex of every member of the group was determined. It was assumed that the amount of aggression shown by a group, in the laboratory or field, would decrease over a period of days as some kind of stabilization was effected. This stabilization could be established by either the development of some social order or some manner of physiological-psychological fatigue. Figures 29, 30, and 31 show the variation in aggression in the three species studied over the period the groups were observed. The graphs show the averaged figures for 5 groups in Paguridae miamensis and 3 groups in Clibonarius tricolor and Calcinus tibicen. The solid circle and solid line represent the number of meaningful, aggressive interactions observed each day. Interaction in which one animal gave an aggressive display to the back of another were not included. The cross and dotted line represents the number of aggressive displays given by members of the group during the observation period of each day. The open circle and solid line represents the percent of meaningful interactions in which an aggressive display was given by one or both of the interacting pair. Figure 29 through 31. Variation in level of aggressive activity over 9 days in groups of Clibonarius tricolor, Calcinus tibicen, and Paguridae miamensis. Groups moved to new observation tank on 4th day and remarked, isolated, reintroduced on 7th day. In all 3 species, the pattern of variation in the aggression of the group is similar. The number of meaningful interactions and the number of aggressive displays decreased during the first 3 days. They then increased upon introduction into the new tank, although not to a level as high as that of the initial day of observation, and decreased even more rapidly until the second alteration, remarking isolation. This was followed by a second increase in these numbers, again not as high as the first day, and a decrease on the last 2 days. The percentage of meaningful interactions in which aggressive displays appeared was rather variable over the full period of observations and showed no consistent pattern. In addition to this consideration of the variation in the aggression of the whole group, the data were examined for the presence of any type of dominance order. Since each shell was marked individually, it was possible to record the interactions of each individual animal during the observation periods. Whenever shell changes were observed, both during regular observation periods and at other times, the change in the identity of individuals was recorded and the data corrected. However, there were probably some undetected shell changes that have contributed to some of the imperfections in the dominance orders. However, it is felt that the 5 repetitions of the measurements in each species provided an adequate preliminary indication of the social order of these crabs. A mathematical measurement of the presence or absence of social organization, whatever its basis, proved to be somewhat complicated. The data were analyzed in the following manner. For each group, the interactions for all the observation periods were considered together. It is realized that any dominance hierarchy would probably not be completely established during the first period, and that it would be advisable to consider only the interactions of pairs after they have interacted at least one time. However, the number of recorded interactions between all the possible pairs in each group is small, and a large portion of these occurred on the first day. For purely pragmatic reasons, it is necessary to consider all the interactions as one set. The percentage of successful interactions was calculated for every member of each group. That is, the number of aggressive interactions in which an individual was dominant, as shown by the retreat of the other crab, was divided by the total number of interactions in which it was involved. The individuals of a group were then listed in order, according to their percent dominance. The upper matrices in figures 32, 33, and 34 show the results of aggressive interaction among the individuals of 3 of the groups. Interaction dominance is red across the matrix and losses are red up. If the groups showed perfect straight-line dominance, and assuming that ranking by percent dominance was the correct ordering procedure, the results of all the fights would appear in the lower right half of the matrix, below the diagonal line. For example, in group 4 of P. miamensis, all the interactions are in the lower right half of the matrix, except one fight in which N lost to L. In another fight, L lost to N. The list of the individuals to the right of the lower matrix and the subsets into which the list is divided was determined by a second procedure. The subsets and the order of the subsets are such that no individual lost directly to an individual in a lower subset. In a straight-line dominance hierarchy, each subset would contain only one individual, and the number of subsets would equal the number of individuals in the group. If the group's aggressive interrelationships were completely at random, unlikely in any group, irrespective of the presence of social order, due to the many physical differences between individuals, the subset would contain all the individuals of the group. Thus, the number of subsets into which the group can be divided could be taken as a measure of social organization. Unfortunately, there are no statistical tables available to determine the probability of chance occurrence of such subset arrangements. The ranking by these subsets has been used here as the correct dominance order in calculating rank order correlations. The order of individuals within the subsets is not meaningful. All crabs in a subset are considered to be equal. The DHS number is the dominance hierarchy statistic value for the group. This was calculated by comparing the interactions of all possible pairs in the group. In a straight-line dominance organization, if A is dominant over B and B dominant over C, A would be dominant over C. Probability that A is dominant over C equals 1. A null hypothesis of no dominance order was assumed, i.e. the probability that A would be dominant over C equals 0.5. The dominance hierarchy statistic presented is the number of standard deviations away from the mean of a binomial distribution of dominance probabilities, which the actual distribution of interactions presents. That is, there is a certain chance distribution of deviations from the probabilities assumed in the null hypothesis. A value of 1.96 or greater is significant. P is less than or equal to 0.05. A value of 2.58 or greater is very significant. P is less than or equal to 0.01. The probability for each distribution is given with the dominance hierarchy statistic. The Fortran program for calculating the dominance hierarchy statistic of a group is shown in figure 35. In addition to the above data, the lower left matrix of each figure shows the distribution of direct and indirect dominance. This covering matrix indicates the individuals that each crab was dominant over either directly or indirectly. That is, if A was dominant over B and B over C, A was considered dominant over C, an X in the matrix, even if they were not observed to interact. The covering matrix includes all possible chains of interactions between all members of the group. The number to the right of each individual's row is the number of crabs it was chain dominant over. The significance of these data will be discussed below. Table 6 presents the statistical data for the other groups observed. Using the subset-determined dominance order, rank order correlations were determined for several morphological characteristics of the crabs in each group, which showed some order, i.e., dominance hierarchy statistic less than or equal to 2.58. The correlation values obtained are presented to the right of the upper matrix for each group and in Table 6. Correlations were calculated between the dominance order and a ranking by cephalothorax length, CL. The crabs were ordered from largest to smallest, and rank order correlations calculated. A second ranking was established for each group according to an index value, SL times CL. This index was obtained by multiplying the length of the cephalothorax of each crab by the greatest length of the individual's shell. Where the rank order correlation value of this index is clearly larger than the cephalothorax length value, it would appear that the size of the individual's shells may have helped to determine their positions in the dominance order. Correlations were calculated to determine if the sex of an individual was important in establishing a crab's position in the dominance order. The individuals were ranked by cephalothorax length and dominance order position within each sex. That is, both the males and females were ranked by size and order within their own sex. The rank order correlations obtained for the intra-sex rankings indicated that sex is not important in determining an individual's position in the social order. For example, the non-sex restricted cephalothorax rank correlation value for group 5 Paguridae miamensis is 0.76, while the average for the intra-sex ranking correlations is 0.44. It is believed that the lower value for this correlation is due to the small number of individuals involved and the resulting increase in chance deviations. In all groups of P. miamensis, the intra-sex correlation values are slightly lower than the standard cephalothorax rank correlation values. The values for the Clibinarius tricolor and Calcinus tibicen groups are the same or very slightly higher than the cephalothorax rank correlation values. Figure 32. Dominance order data for observation group 4 of Paguridae miamensis. Upper matrix shows results of aggressive interactions between members of group. Dominance red across, losses red up. Dominance hierarchy statistic indicates amount of order in groups interactions. Lower covering matrix indicates X, individuals over which each crab was chain dominant, subsets such that no individual is dominated by an individual in a lower subset. Figure 33. Dominance order data for observation group 1 of Clibinarius tricolor. Figure 34. Dominance order data for observation group 1 of Calcinus tibicen. Fortran program for social order analysis. Dimension in 20, 20, L 20, 20, M 20, 20, N 20, 20, KUM 20, TAG 20, TIT 1 LE 12, 100. Read input tape 5, 101, title I equals 1, 12. 101. Format 12A6. Write output tape 6, 101, title I equals 1, 12. Do 102, I equals 1, 20. 102. Read input tape 5, 103, TAGI in IK, K equals 1, 20. 103. Format A6, 201L. Do 105, I equals 1, 20. Do 105, K equals 1, 20. If in I, K, 104, 104, 110. 104 in IK equals 0. L, IK equals 0. Go to 105. 110 L, IK equals 1. 105 M, IK equals LIK. Write output tape 6, 106. 106. Format 21HOID win matrix //. Do 107 I equals 1, 20. Do 3 I equals 1, 20. Do 3 K equals 1, 20. K temp equals 0. Do 1 J equals 1, 20. 1 K temp equals K temp plus L apostrophe, J asterisk M J, K. N I, K equals 0. If K temp 3, 3, 2. 2. N I, K equals 1. 3. Continue. Sense light 0. Do 5 I equals 1, 20. KUM I equals 0. Do 5 K equals 1, 20. KUM I equals KUM I plus N I, K. If M I, K minus N I, K 4, 5, 5. 4 M I, K equals 1. Sense light 1. 5. Continue. If LCOP minus 2, N, 6, 9. 6. Count equals 0. Num equals 0. Do 8. I equals 1, 20. Do 8. K equals 1, 20. If N, I, K 8, 8, 7. 7. Num equals num plus in I, K equals in K, I. Count equals count plus in I, K. 8. Continue. If sense light 1, 10, 11. 10. Continue, go to 100. 11. Write output tape 6, 12. 12. Format 40H ID covering matrix dominance //. Do 13 I equals I, 20. 13. Write output tape 6, 14, TAGI, M I, K equals 1, 20, KUMI. 14. Format 1x, delta 6, 20 apostrophe 1, 17. X equals num, Y equals count, Z equals Y minus X divided by 2 over square root of X divided by 4. Write output tape 6, 15, Z. 15. Format 34HO, dominance hierarchy statistic equals F5.3. Go to 100. End. 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0. Figure 35. Fortran program for calculating dominance hierarchy statistic and covering matrix of interactions of members of a group. Table 6. Dominance order statistics. A table I am not reading. Figure 36. Size relationship in attacking and defending crabs in shell fights. Clibonarius tricolor.